Hello, my name is Nicolas Escobar. Welcome to our presentation today. I will be handling part one of this presentation, while my partner Carlos Velez will be handling part two. This presentation may be a two-part video, just in case Zoom does not merge our presentations together. To start with, our presentation will be based on real-time systems in embedded systems and their applications. So I'll start by going over what is a real-time system. A real-time system is a system that responds varies based on the current situation happening and the specified deadlines. An example of a real-time system would be your car sending you a low fuel signal. So you see the low fuel popping up on the dashboard. There are two types of these. We have hard real-time systems, which would be if the system fails to meet the deadline, a severe incident could occur. This would be an air traffic control tower not communicating to the planes efficiently, causing a delay in their landing, which would push the whole landing process back and may cause an accident in the airport. And then we have soft real-time systems, which this is where it fails to meet the deadline. It doesn't do anything severe. It just be minor setbacks, such as a DVD player failing to meet its video deadline. You may have the audio a few frames ahead of the video, so you'd hear what's happening before actually seeing it. And then some examples of real-time embedded systems would be controllers in assembly line, smart systems, and traffic lights. Some other examples would be a missile embedded with a tracking system. The tracking system would be the real-time embedded system in this case. Some more examples we have would be your fax machines, your security systems, your household items, medical equipment, traffic management. More in-depth example would be a cardiac pacemaker in the car. The batteries and the converters receive energy from the alternator. This will then get transferred to the microcontroller and go to the swift drivers and then place these into the airbags for when an accident occurs. What makes a real-time embedded system would be the hardware and software of an embedded system. So the operating systems, the CPU, the RAM, the processors, the input output ports, etc. And then real-time computing, which would be computing based on what is currently happening in real time. So in this presentation, we'll talk about 5 industries. I will handle the first 3, and then my partner will handle the second 2 industries. So the first industry I'm going to talk about is the automotive industry. So the main purpose of RTESs in the automotive industry is to provide comfort and safety to the driver. These features would be regenerative braking, GPS, tire pressure monitoring, etc. These features are seen in both petroleum and electric cars, but they are more commonly seen in electric cars due to be able to have a fully integrated real-time embedded system and a real-time operating system, RTOS. On the engineering side, you mostly see these systems in the multi-core system of the car because that's where the OS is. And this allows the vehicle to form a communication network within itself. So that's how you would know your tire pressure, low battery, low fuel, and also form a communication network with other vehicles in the surrounding area in order to calculate traffic flow on the GPS, nearest gas station if you're running low on fuel, restaurants, etc. It's also will alert you of potential hazards or traffic, things that would keep you unsafe in a vehicle. I said most of these features are located within electric cars, but some are also in petroleum-based cars, such as regenerative braking, GPS, DVD players, etc. So here we have a example of an embedded system in automobile. Your real-time systems here would be your GPS, your tire pressure, your instrument clusters, your display. Your adaptive cruise control is a big one that uses the sensors in the front of the vehicle, your heads-up display, your parking assistant, etc. Leave this slide here for a few seconds just so you can see the other systems involved. And now a more in-depth engineering example. Figure here on the left shows how regenerative braking takes account to real-time systems. So in the design phase, you have your motor and your braking profiles, your voltage and current pairs, and that gets combined with your converter and battery model to give you a current cap. So when you're running your regenerative breakers, it will read the voltage and current in your motor, plug that into the current cap formula and the current battery formula in order to calculate how much energy is being converted from electrical to kinetic to fill your braking storage to perform regenerative braking. And the figure on the right would show you the differences between charging current and charging power in real time. So the top figure shows you the battery constraint, this using the super cap first, and then the proposed model of combining both systems together. Proposed model looks a lot better than using one or the other. The second industry I'm going to go into is the manufacturing industry. The main purpose of RTSs in the manufacturing industry is to ensure production goals are met without much defect, without much time delay. You mostly see these in controllers and assembly lines, such as the robotic arms, but also in their quality inspection cameras and monitoring systems. So here on the right, I have a schedule example to kind of give you an idea of how a schedule works. The top shows you the schedulability for a task, followed by the description, followed by how much control is needed, followed by comfort, followed by error tolerance, and then followed by sustainability for learning. This is mostly used when you're training new machines. This is the algorithm you typically follow. When using real-time embedded systems, for examples in robotics, you'd use them for training so the robot would become more aware based on the error tolerance and its sustainability for learning. So if you look at the tutorial, you would see that the average task load is decreasing per period due to this learning. So here I have a more in-depth example. This would be a manufacturing assembly line. So to make this in-depth example pretty simple, let's say you have three systems: your pre-processing, your processing, and your post-processing. Each system would have its own real-time embedded system. Someone would be responsible for control feed, washing, peeling, washing, peel dewatering, inspection, then slicing, cold hot water, dewatering, and the third system, frying, flavoring, and packaging. By doing this, you're able to set tasks and use earliest deadline first to keep the system under control. This does make it more of a hard real-time system, but if I go into the example of processing, let's say you set everything with a period of 10 here, you might do slicing takes 2 seconds, cold and hot water takes 5 seconds, and dewatering takes 3 seconds. By doing this, they all have the same deadline, and you can set task priority. But in some cases, you may have to speed up the process. So you might have to slice twice before you're able to cold and hot wash. This is when you use EDF. You might have slicing is done, or you may have to re-slice is actually the better way to rephrase this example. So you might have slicing with a period of 5. This takes 2 seconds. Then the cold and hot wash takes 5. It would have to re-slice, and if you set the dewatering with a period of 15, it would do the dewatering last after doing 2 loads of slicing and 1 load of cold and hot wash. All right. On the next page, we'll go into quality inspection. So this shows you a quality inspection camera. As toys or other products are moving down the assembly line, this would scan the code in the to see if it's in the correct spot. If not, it would send it down the defect line. This uses real-time embedded systems because it has to be able to determine what product it's scanning. Not just one product goes down these assembly lines. Eventually, they do get mixed in, but also each part would have its own serial code. So it would have to scan to make sure the code is in the correct place and make sure the part is in the correct place. And then these systems are also placed into robotics optic systems in order to assess the quality of more parts, but also these can go more in depth into safety issues, such as checking how much the speed of a running assembly line, the precision of the robotic arms, etc. So now the final industry I'm going to talk about will be the civil industry. Real-time embedded systems we've talked about are in numerous places. They are in your household items, traffic management, etc. Where you most commonly see these would be public infrastructure and monitoring systems. And the example I'm going to use is traffic lights and motion detectors. So here the figure on the left shows a traffic light schedule. You got the pre-time state, the evaluation state, and then because a traffic light is for a two-way road, you also have a second pre-time state. This pre-time state would be if you're going south to north, this would be north to south, east to west, west to east, etc. So the way a traffic light and camera system works together is the cameras would scan the roadways. Let's say I have a traffic car at this point here, this truck here, and the light is red, and I have no oncoming traffic here. The cameras would communicate with the traffic light. The camera placed here would look at the roadway, see no oncoming vehicles, but the camera here would see one vehicle stopped here and two more coming. In order to reduce the flow of traffic, this camera would communicate to the truck, to the traffic light, in order to change this light green to have this truck go on its way, and these as well, since there is no oncoming traffic. This reduces the flow of traffic and increases public safety for civilians on the roadways and pedestrians on the walkways. And this concludes my presentation here. The final thing I want to talk about would be the cameras. This figure on the right shows you the traffic light camera scheduling, how it would work for a real-time embedded system. And that is about it. I will now pass the presentation to my partner, Carlos Velez. He will talk about the last two industries and the conclusion of our paper. Thank you, and I appreciate your time.
Hello, I'm Carlos Velez, a purchase product engineer working for the national labs in Kansas City to develop and manufacture nuclear warheads for our country's war reserve. Today, I will be presenting real-time embedded systems for the security industry and the communications industry. As computational power continues to increase, systems become more advanced, requiring intricate combinations of hardware driven by embedded systems. Here we discuss security concerns that may arise while using embedded systems and what the industry is doing to mitigate risks. First, I will introduce some security challenges and discuss some attack vectors that may be used to compromise the system. I will then suggest best practices for mitigation and give a deeper dive to one security architecture that is in use today. Finally, I will present an example using the security architecture. Some security challenges that present themselves to embedded systems are power and memory limitations, connectivity and access control, and physical exposure. Power and memory is a major challenge to overcome, seeing that many embedded systems are designed to carry the minimum required power and memory to run the embedded system. With the addition of security applications, resources can be strained, limiting the computing power of the real-time operating system and increasing system latency. Another security concern arises from connectivity and access control. When a malicious party is granted access to a network, they may choose from an entire host of attacks to either hijack a session or deny service to the network. Lastly, Physical exposure to a system will allow an attacker to experiment with the hardware and software, giving them an opportunity to learn what attacks may be successful. This can be mitigated with some tamper-resistant software techniques like secure boot, which will only grant the operating system control of the software via firmware drivers that ensure the validity of signatures of the software. Attack vectors are usually found in two main categories: software-based and network-based. Software-based attacks come in the form of malware, brute force attacks, and buffer overload. Malware attacks on real-time embedded systems can be used to gain access to secure data on the software or overclock and damage a system. An example of this would be the Stuxnet attack that was used to take over the SCADA system of an Iranian uranium enrichment facility. This attack isolated the centrifuges and ran them above proper operating speeds, destroying 10% of the centrifuges in the facility. Brute forcing is the act of trying every combination of password to access a system. With memory and latency challenges being what they are, shorter passwords are often used, which can allow brute force attacks to become more feasible than normal. Lastly, buffer overflow can be used to insert exploits into memory that may elevate their access credentials. Network-based attacks can also be used against real-time embedded systems. A man-in-the-middle attack is used to hijack a session and intercept trafficked information from an unknowing user. This can be done with a simple piece of hardware like a pineapple. Distributed denial of service, or DDoS attacks, can cripple a network, making them unusable to anyone on the network. A DDoS attack is similar to a DOS attack or denial of service attack. The only difference is the DDoS attack is usually using a zombie swarm, which is an army of infected computers used to overload a system with verification requests. DNS poisoning is when an attacker corrupts a domain name server that translates IP addresses and human-readable domain names. This can be used to reroute traffic at the will of the attacker. Some of the best practices to mitigate system vulnerabilities is to use safe and secure language and coding practices. This can be anything from using a sandbox to avoid buffer overload or learning to develop code with a more secure architecture. You can also enable secure boot requirements. This was previously discussed, where a firmware driver must first verify a system signature before granting control to the operating system. Another good practice is to disable non-essential services. This eliminates the potential for attackers finding backdoors into unauthorized data storages. Lastly, a system architecture that partitions data based on a security level may be used to eliminate bleed over to a system that does not meet the security requirements of a higher system. When developing a system for the military or government, it is often required that the system may be used to access or transmit security information. As such, the system must be able to identify the level of security and partition it appropriately. The levels of security include official use only, confidential, secret, top secret, and a host of other classifications. As such, top secret information cannot be transmitted on a system rated to secure information. Therefore, a partition or firewall must be used to segregate the more sensitive information. Multiple independent levels of security, or MILS architecture, does exactly that. It is a technique that builds multiple bins that work independently from one another and can be customized to the level of security required for its use. This allows changes to be made to a specific level without affecting the other security levels. An example of this can be seen in modern-day fighter jets. The Generation 5 F-35 has a suite of avionics and communications platforms that collect various classification levels of data. In order to share less sensitive data with members in the battle space, a partition must be created so that more sensitive data cannot leak out. As with most complex architectures, communications are one of the most integral aspects of a given system's function. The need for reliable communication systems stems from the balance of multiple sensors and actuators while monitoring the system's current state. As such, with regard to real-time embedded systems, the communications industry is not an isolated industry existing in a vacuum, but a monolithic enterprise distributed among all facets of industry. Therefore, the discussion on real-time embedded systems in the communication industry will focus on the application of communications in an embedded real-time system. Here, we will discuss various methods of communication, inherent vulnerabilities, and how the industry uses communications. We will then take a look at Goose protocol techniques used in modern power substations and vehicular ad hoc network architecture. Finally, we will explore some mitigation techniques that may be used to address the security concerns found in these two industry applications. There are various means of communication a network may use to transmit data from place to place. This requires the use of routers, switches, access points, and antennas that interconnect a network and the numerous clients working on the network. Hardwired systems may seem the most secure network architecture. However, this system may still be vulnerable to attack. These attacks often come in the form of physical attacks, and therefore a great deal of physical security is required to mitigate risks to the system. One such attack would be the insertion of a rubber ducky or keylogger into a port in the system. While hardwired, network devices such as switches may offer an attacker the opportunity to infiltrate the system without the knowledge of any system administrators. The attacker can then retrieve sensitive password information or insert a malicious code into the system. Access points such as wireless routers can also offer an attacker a wealth of opportunity. The wireless nature even provides the attacker with an added benefit of anonymity, since the attacker need only to be in the vicinity of the access point, eliminating the need for physical access. As previously discussed, the attacker can then hijack a session using a man-in-the-middle attack or deny service to the network completely. Finally, with the use of a wide area network, or WAN, a network must transmit data over a long distance to control time-sensitive equipment. This is the case with power substations that use intelligent devices. Power plant and substation controls can be attacked via the antennas that allow open transmission of data to and from server-client communications. Some vulnerabilities to communication systems using real-time embedded systems stem from the time-sensitive information, communication protocols, and encryption. These all lead to increased system latency, which in turn limits the efficacy of time-sensitive information, which can endanger the overall use and safety of the system. Time-sensitive information is especially a concern with hard real-time embedded systems, which have stringent deadlines that must be met for the proper operation of the real-time system. If these deadlines are not met, there may be a catastrophic failure to the system accompanied by safety concerns that may arise. For example, if an elevator does not receive a message of a blocked door, it may begin changing floors with occupants in the doorway, leading to almost certain death or dismemberment. For this reason, communication protocols must be able to quickly relay information while maintaining a level of security that avoids malicious attack. The hardwired nature of an elevator control system would be a prime example of a proper balance between security and system latency. The encryption protocol for a given message is not stringent because the attacker is not afforded easy access to the network controlling the elevator floor and door status. Therefore, it can be trusted that the elevator will not operate with occupants in the threshold. The industry uses distributed architectures to hold information static for a time, process said information, and transmit information when required. This can be used to provide dependability, composability, scalability, maintainability, and allow processing closer to the data source. Thus, errors can be contained within nodes, systems can be designed as integrated subsystems, Additions can be readily made to the system in a modular configuration, and data can be processed by intelligent sensors and actuators. As such, time across the network can be simplified with proper scheduling and a centralized clock at each node. For example, a smart HVAC system could be designed to maintain the habitability of an individual room by placing various sensors in each room. Each sensor then reports to a client in the room that stores and processes the temperature, humidity, and air quality of the space. A server can then cycle through each client and therefore each room to collect the required information. Once collected, the server can then send control information to the central HVAC system to manipulate each room's dampers and fans accordingly. The system can then be fitted with certain event-triggered communications that override the normal message traffic for events such as fire or poisonous gas. As previously mentioned, smart sensors and actuators have become ubiquitous in modern-day smart grids and power substations. The two main buses on a substation, the station bus and the process bus, communicate using an event-triggered communication, which in this case is the GOOS, or Generic Object-Oriented Substation Event Protocol. This is done by using a smart sensor to monitor the plant. For example, if the sensors detect an event such as overcurrent on the bus, a message is sent via the station bus to actuators and switchgears to open a circuit. This is accomplished using logic nodes in the intelligent electronic device. The smart sensors then continue to monitor the station to acknowledge the open circuit. Once the fault is cleared, the sensors can then send another message with the GOOS protocol to close the circuit. However, an issue with this protocol is the need for very low latency. Seeing that overcurrent can be very detrimental to the material condition of the plant, the actuators must trip within 4 milliseconds of the fault. As such, encryption protocols are not currently being used for such messages. Therefore, the system is very open to malicious activity. Research into lighter encryption methods is being conducted, and Siemens has recently patented a new method of group key generation in an attempt to improve system security with regard to GOOS message models. Another network that is growing in popularity is that of the Vehicle Ad Hoc Network, or VANET, which will allow vehicle-to-vehicle communications as well as vehicle-to-infrastructure communications. The spirit and intent of this network is to increase safety and efficiency of our roadways with more intelligent sensors and vehicles. Some ways this will be used is by warning drivers of hazardous road conditions, road closures and detours, and other emergency events like a hard braking driver ahead. However, this will require increased security measures as this is a new attack vector for criminal activity. This network can be prone to civil attacks and counterfeit event-triggered communications like an alert of a hard braking driver ahead, causing an unauthorized road closure. The figure below shows three various network topologies. The first is a vehicle-to-infrastructure topology, the center is a vehicle-to-vehicle topology, and the last is a combination of the two. Thank you very much for listening to our presentation on real-time embedded systems and their applications.